So today it is our pleasure to invite Professor Takumi Abe to give a talk about his research. Professor Abe-san, he got his PhD in 1991 from the University of the Electrocommunication in Tokyo, Japan. So now he is an associate professor at Department of Solar System Science and in Institute of Space Astronautical Science, Japan Aerospace Exploration Agency. So he is based on the ionosphere research. So today his topic is science instruments to observe the ionosphere thermal plasma on the space-based platform. So let's welcome Professor Takumi Abe. Okay, you can start.
Okay.
So should we record? Start recording.
Okay.
Okay. Please.
Okay. So thank you very much for your introduction. I'm Takumi Abe. I'm working at the Institute of Space and Astronautical Science of Japan Aerospace Exploration Agency. I'm very honored to give a talk today. Title of my talk is Science Instrument to observe the ionospheric thermal plasma on the space-based platform. In particular, I would like to focus on Langmuir probe measurements. Okay, this is the outline of my talk today. My presentation consists of 6 topics. First, let me start with an introduction of Langmuir probe. Next, I want to talk about the Langmuir probe equation for electron temperature and density estimation. Then, I would like to discuss measurement accuracy and actual implementation of Langmuir probe. Also, I would like to introduce data from recent sounding rocket experiment in which Langmuir probe played very important role. Finally, let me explain our recent development of a new instrument. First, introduction. During my talk, if you have questions, please ask me anytime. Okay. Introduction. So as you know, many science instruments have been used to observe ionospheric plasma. Langmuir probe to estimate electron temperature and density, ion density, and sometimes energy distribution function. Impedance probe, resonance probe, retarding potential analyzer for ion measurement. Ion drift meter was also installed many times, like the SP satellite. And suprathermal and thermal ion mass spectrometer on Japanese Akebono satellite. Called thermal plasma analyzer. This instrument was installed on Swedish Flare satellite and Japanese Nozomi spacecraft. Langmuir probe is known as a simple and conventional instrument to understand basic characteristics of thermal plasma in the ionosphere. And as you know, this instrument has been frequently installed for more than 5 decades on sounding rockets and satellites. In this talk, I would like to focus on DC Langmuir probe. As many of you know, Langmuir probe has been flown on spacecraft since the initial stage of space exploration in 1950s. So for more than 50 years, Langmuir probe has been used to know fundamental and important information on the thermal plasma, mainly in the ionosphere. This instrument can provide electron and ion densities, electron temperature, and spacecraft potential in the ionosphere. To have these parameters, Langmuir probes have been installed extensively on sounding rocket and satellite, such as Japanese S310 and S520 rockets, sounding rockets, and Japanese satellite, US, United States Explorer satellite, Arrowhead, ISIS-1 and 2, atmospheric explorer series, D2, and Pioneer Venus orbiters. And there is no general theory of Langmuir probe which is applicable to all the instrument conditions because it depends on probe size and geometry, so plasma density and temperature, platform velocity, and so on. And in thermal plasma measurements in space, platform potential is very important. So before entering into equation to estimate the temperature and density, let me explain about the platform potential. Because a certain DC voltage is applied to the instrument with reference to the platform potential. In general, spacecraft is charged to negative because the incident electron current is much larger than incident ion current, which is called floating potential. And floating potential is expressed by this equation. And floating potential is known to depend on many parameters in space. For example, a ratio of spacecraft velocity to electron and ion thermal velocity. Second, hot electron flux emitted from spacecraft surface due to sunlight. Third, influx of energetic electron to spacecraft surface and secondary electron flux generated by the incident electron. And in actual spacecraft, floating potential is within 2 volt. This is the normal case. But in particular case, for example, if positive potential is exposed and the electrons are collected by this positive potential, floating potential could be minus 10 volt. And if many energetic electron influx exists in shadow region, floating potential may be up to 1 kilovolt. So this is very significant. And next, let me explain equation to estimate electron temperature and density briefly. I think this equation you already know, but let me explain briefly. These are well-known equations about incident current to the probe in the Langmuir probe measurement. So random electron current at the plasma potential is expressed by this equation, and electron current at the plasma potential is expressed by this equation. And next equation is a general expression of electron current in the retarding potential region for electrons. So this retarding potential retarding region. And then electron temperature can be derived from the gradient of electron current in logarithmic scale, this one. And the electron density is derived from random electron current at the plasma potential by using this equation. So when logarithm of electron current linearly changed with probe voltage, which means velocity distribution is Maxwellian, it's possible to estimate electron temperature and density. And the equation in previous slide is held in laboratory plasma. However, ion current should be treated differently in space. So let me explain how we should treat the ion current on space-based platform. So usually, ion current at plasma potential is expressed by this equation, and considering thermal ion measurement on the very fast moving frame, such as Earth orbiting satellite, and if apparent bulk velocity due to rocket velocity, spacecraft velocity, is much larger than thermal ion velocity, the ion current is expressed by this equation. So when negative voltage is applied to the probe, ion sheath is formed, as you know, and apparent surface area of probe will be increased. So I use the S dash like here. And next, I would like to talk about measurement accuracy in Langmuir probe. This is also well-known characteristics in Langmuir probe measurement. It is possible to assess the measurement accuracy by examining consistency between Langmuir probe theory and measure the voltage current relationship via curve. If the distribution function is Maxwellian, electron current in the retarding potential region must be expressed by a simple exponential relationship of the electron temperature. On the contrary, if the retarding portion cannot be considered as Maxwellian, the measurement might be invalid. However, we have to be very careful with interpretation of probe current. For example, background current due to photoemission from the probe may change the electron current. This is particularly significant when the electron density is low. Again, measurement accuracy. You may suppose that the measurement accuracy in the Langmuir probe depends mainly on the validity of fitting to observed VI curve. However, this is not always true. More exactly speaking, measurement accuracy is determined by not only the validity of the approximation to the VI curve, but also by shortcomings in design and implementation. So it is possible that measurement error arises from these causes. First, inadequate position of the probe in the spacecraft or rocket body. Second, contamination of the probe surface. I will talk about this later. And third, failure to adapt a probe which has uniform collector surface material. Then failure to design electronics to resolve VI curve. 5. Failure to assure that the spacecraft or rocket serves as a stable potential reference for the measurement. So we should be careful about these issues.
So Abe, I have a question.
Yes. Okay.
So do we need to consider about the solar wind, like the interaction with solar wind, like the solar mass, solar activity, if they have such a big event?
I'm sorry, I couldn't understand. Could you repeat again?
I mean, if the solar activity,
Solar
so
activity.
yeah, the solar wind interaction with the iron atmospheres. Do we need to consider this accuracy or this when we estimate this?
I'm sorry. Are you asking about solar wind or sunlight? Effect of sunlight or solar wind? Which one?
The solar wind.
Solar wind. Oh, we don't care about the solar wind because usually solar wind particles cannot enter the ionosphere.
Okay.
Any other question? No? Okay. So let's move on to the next topic, which is implementation of Langmuir probe. So usually we spend a great amount of time to implement Langmuir probe on space-based platform rather than analysis of Langmuir data itself. We have to think about the many issues when we try to implement Langmuir probe. So I'd like to spend lot of time for this implementation. Several types of probes have been used for Langmuir probe measurements: spherical probe, cylindrical probe, and planar probe. So each probe has its own strengths and limitations. in recent years, we have installed spherical probe and cylindrical probe on sounding rocket. We installed planar circular probe on spinning satellite. When we decide the shape of a probe, we have to consider several external conditions. First, shape and attitude of spacecraft to avoid satellite wave effect. Second, velocity vector of spacecraft to avoid wave effect and the influence of ion current. And third, sunlight direction. As I already told you, it may have influence of photoelectron on plasma measurement, probe measurement. And the dimension of probe is also important parameter. When we decide a size of probe, we have to consider divide length, mean free path, cis width, and area ratio of spacecraft and probe surface is also important parameter. Usually, a type and dimension of the probes are designed for special limiting cases, such as OML, orbital motion limited theory, or SAL, cis area limited theory. For the OML condition, probe radius must be small compared with cis thickness. In contrast, for the SAL condition, probe radius must be large. Probe dimension must be large to meet the SAL condition, and it is sometimes too big to be installed on satellite or rocket. On the other hand, it is not so difficult to make the probe dimension small enough for the OML condition, because the by length is in the order of 1 centimeter in the ionospheric F region. Therefore, satellite Langmuir probes have usually been made small enough to remain the OML theory. In particular, cylindrical probe had been more frequently used because its radius can be made small enough to remain the OML, while its length can be made large. And as already told you, platform potential is a very important parameter to interpret voltage current curve. So voltage sweep should cover appropriate range so that spacecraft potential can be determined. If the spacecraft potential cannot be determined, we cannot calculate the energy distribution. And some people use a potential control against satellite to measure the parameters of thermal plasma, particularly when spacecraft is expected to be negative. This is effective, particularly in the plasma with very low density. But in this case, it is important to confirm that the measured parameters are not affected by the potential control system. And the next one is spacecraft wake effect. So as you know, spacecraft wake is formed at the backside of a moving direction. In the wake region, electron velocity distribution is different from that outside. This means that velocity distribution is distorted in the wake region. In this case, it is important to find how to avoid wake effect and a way to obtain unaffected electron temperature. The possible way to put the instrument on boom deployed from the spacecraft to decrease an effect as much as possible. Okay. First topic is probe surface contamination. Let me introduce how we avoid probe surface contamination. Actually, this method was originally developed by Professor Oyama. Of course, you know Professor Oyama. It is important to remove contamination layer on the probe surface because it may cause a hysteresis in the probe current. In our case, in order to remove contaminated layer on the probe surface, cylindrical electrode sealed in the glass tube is baked at a high temperature like 200 Kelvin, 200 degrees Celsius, in a high vacuum condition for more than 24 hours so that it can get out gas from the surface. After that, the probe is tipped off from the vacuum system in such a way glass sealed clean probe can be kept for a long time. Then, during rocket flight, glass is broken by a spring-actuated sharp edge during rocket flight. 1 second later, from the glass cutting, probe is deployed in direction perpendicular to rocket axis. So glass is removed from the probe by a centrifugal force due to rocket spin, and then clean probe is exposed to the plasma outside of rocket sheath. So in this way, we start measurement of thermal plasma. And next, I'd like to explain other issues of laminar probe implementation. So we have to keep the following issues in mind. because these are critical in laminar flow measurement. First, flow must be placed in the proper position, and should be placed outside the spacecraft sheath and wake. Secondly, we have to make an effort to keep the work function on the probe surface to be uniform. And the reduction of geomagnetically induced potentials should also be taken into account. For example, potential gradient of about 300 millivolt per meter is possible when spacecraft moves at high velocity through magnetic field. So if probe diameter is 10 centimeter, so maximum potential difference inside the probe will be about 30 millivolt. So we cannot ignore this voltage. So we need to decide adequate range and resolution for applied voltage and the probe current. So these parameters should be chosen by considering spacecraft velocity, spin rate, and available telemetry rate for the data transmission. Okay. Next, I'd like to show you a practical specification of our laminar probe. Left side panel shows parameters to be decided and things to note. Right side panel show practical specification of our laminar probe system. Usually, we apply a triangular sweep with amplitude of 4 volt peak to peak. Sweep rate is usually 10 Hz or lower. In other words, we can get 20 sets of VI curve in 1 second. And the voltage step is about 0.01 volt because 4 volt is divided by 320 points. And the flow scale in low and high current gain is set to 10 and 0.5 microampere. We use these specifications when we install laminar probe for sounding rocket. Okay, so next, as I already told you, laminar measurement have several things to be careful about. But next, let me explain how we try to overcome the potential problem. So in my presentation I have given today, it was assumed that spacecraft potential is kept constant. However, this is not true in a particular case. This slide shows VI characteristics obtained in the auroral region by thermal electron energy distribution instrument on Japanese EXOS-D satellite. So as you see, the measured current repeated increase and decrease during one voltage sweep. This is impossible in steady state plasma condition. So these data were probably caused by a fact that the satellite potential was changed by precipitating electron incident to satellite surface. So, as I already told you, on the normal situation in the ionosphere, spacecraft potential remains within a few volts. In contrast, it is possible for the potential to change rather than 10 volt in the polar region, auroral region. So the degree of charging can become larger when the active experiment is carried out on the spacecraft. So voltage voltage step of 100 volt with a fine step to cover big potential change like this is not practical, unfortunately. So we need to develop Langmuir Pro, which can properly work on spacecraft such that its potential significantly changes. So I'd like to say finding differential potential is a key when spacecraft potential may change significantly. And plasma potential, as already explained, plasma potential exists in the boundary between number 1 and number 2. And the gradient of electron current, actually, logarithm of electron current becomes largest in the lower side of plasma potential. So we decided to take a shape sequence as described here. First, probe voltage is swept in the wide range from 0 to 100 volt, for example, with a rough steps. It is called V1 shape. Second, difference potential is defined at the potential at which gradient of probe current becomes maximum in the V1 sweep. Then, finer which voltage sweep covers from -3 to +1 volt based on the reference potential. Okay, so electronics having such a function was developed in our laboratory, and we have conducted a demonstration experiment by putting such a Langmuir probe inside the space plasma chamber to simulate spacecraft charging. So bias voltage of several tens of volts was applied to the electronics. So this slide shows several results from this laboratory experiment. So in each figure, horizontal axis shows probe voltage, and vertical axis shows probe current. So red plus sign represent difference potential, which was calculated by logic group implemented in the electronic circuit board. So we can confirm that the estimated reference voltage is enough close to the given bias voltage. So next slide shows a comparison of bias voltage, reference potential voltage determined by electronic circuit board, and plasma potential estimated by our calculation. As you can see, in almost all cases, determined reference potential is close enough to the plasma potential within 1 volt. This means our logic can successfully determine the reference potential. However, in these three cases, surrounded by red frames, the reference potential was estimated to be about 2 to 3 volt larger than the plasma potential. The reason for this difference may be that our calculation detected a steep gradient in the electron saturation region. As you know, electron saturation current is very big. That's why a small variation in electron saturation current is picked up. So next, let me show you our Langmuir probe data, actual data we have obtained in the past experiment. First, let me introduce Japanese sounding rocket experiment S52026, which was conducted in January 2012. The science objective of this experiment was to perform a comprehensive observation of particle and field to investigate upper atmospheric dynamics through neutral plasma coupling. So main target traveling ionospheric disturbance, small-scale plasma irregularity, neutral wind, and plasma drift. A total of seven science instruments were installed on this rocket. And this slide shows raw data of Langmuir probe measurement from 50 to 100 seconds from the rocket launch. Green line represent low gain data, and red line shows high gain data. At this time, voltage sweep rate was 5 Hz, so we can get 10 sets of VI curve in 1 second. And next slide shows voltage versus current curve. In these plots, one data set consists of 2 panels. In left panel, probe current in vertical axis is presented as a function of probe voltage in horizontal axis. And right panel shows semi-logarithm plot of electron current. As you see, we can confirm that the electron current is approximated by a straight line, which means the electron velocity distribution was in Maxwellian. And another Sandy rocket experiment I'd like to introduce is S52029 experiment, which was conducted in August 2014. Science objective of this experiment was to study 3D-dimensional structure of sporadic E layer in the mid-latitude ionosphere. So in this experiment, 3 complementary measurements were carried out to elucidate 3D structure of electron density. Those are magnesium plus ion imager, impedance probe and Langmuir probe, and low frequency and medium frequency wave receivers. And again, this slide shows the voltage and the current curve from this experiment. And these data were obtained at from 68 to 68.4 seconds from rocket launch. So these data were also analyzed by a standard algorithm for electron temperature and density estimation using least squares fitting to electron and ion current. Electron temperature and density were calculated without any problem. However, I would like to introduce interesting data set was obtained during this experiment, which is related to the sporadic E layer. So this slide shows VI curves from this experiment. Please note that we can recognize a difference in VI curve between upward voltage sweep and downward voltage sweep. You may suppose that this difference might be due to hysteresis effect related to probe surface contamination. However, that possibility is denied because upward and downward sweep data are almost identical in the top panel, like this. So we believe that this difference is evidence that the electron density changed during voltage sweep period when the rocket passed through sporadic layer. So as evidence, as the rocket is approaching to the center of sporadic layer, current in downward sweep is larger than that in upward sweep. In contrast, as the rocket is moving away from the center, the current in upward sweep is larger than that in the downward sweep. So in such a data set, we have to apply a different algorithm to estimate the correct electron temperature and density. So finally, I'd like to introduce our recent development of a new science instrument to observe ionospheric ions. So as an instrument to measure physical parameters of thermal ions in the ionosphere, retiring potential analyzer and ion drift meter are well known. As you know, RPA can analyze ion energy by applying voltage to the mesh grid, and it provides component of ion drift velocity perpendicular to the sensor plane, as well as ion density and temperature. On the other hand, in case of ion drift meter, it is possible to estimate the incident angle from a ratio of multiple collector plate. So this provides a component of ion drift velocity parallel to collector plane. So we thought it would be possible to develop an instrument which provides ion drift velocity vector by combining these two instruments. So the next slide shows appearance and structure of our new instrument. We will have RPA section in the first stage to get the normal component of ion drift velocity and current collector in the second stage. So the well-known IDM instrument consists of 4-segment collector. In contrast, we increase the number of planar electrode for ion current to get better angular resolution of drift velocity estimates. Before fixing our instrument design, we carried out a numerical simulation on our instrument. We built a collector electrode and electric field with a mesh grid in the simulation space. Then we inject ions, which are expressed by Maxwellian distribution, actually drifting Maxwellian distribution of a given velocity and temperature to the instrument. Then we calculate ion current for each electrode. After that, we analyze the current distribution for respective case of various combination of ion drift velocity, incident angle, and temperature. This slide shows several examples of ion current distribution of multiple collector electrodes. Top left panel shows distribution for drift velocity of 1200 meter per second, temperature of 500 Kelvin, and incident angle of 0 degrees, so normal incident. Other figures show distribution for different incident angles, like 24 degrees and 48 degrees. As we expect, position of peak current is identified in the different locations. Next slide explains how to estimate ion drift energy from RPA profile of ion current. In each figure, the horizontal axis shows RPA voltage, and the vertical axis indicates differential of ion current. Identified peak energy is compared with assumed energy. Results seem consistent, but the estimated energy is slightly lower than given energy. The reason of this difference may be related to the fact that energy is calculated by peak energy to get it more accurately, we need to treat as the distribution of ion velocity. Then I would like to explain a laboratory experiment with our ion drift velocity analyzer. We try to evaluate basic performance of our developed instrument while the ionospheric plasma is simulated inside the vacuum chamber. Plasma was generated by using a back diffusion type plasma source. So we put both instrument sensor consisting of RPA and sensor electrode and preamplifier. This slide shows an example of two-dimensional distribution of ion current measured by multiple collector electrodes. At this time, instrument was put towards the plasma source so that the ions are coming perpendicularly to the RPA mesh plane in the instrument. So as you can see, peak current is found to exist in the center of electrode, as we expect. So this is the last slide of my presentation summary. Maybe I don't need to repeat because I already told you about these things. So that's all of my presentation. Thank you very much for your listening.
Okay, thank you, Professor Takumi Abe-san. So very nice talk. So any question from the audience? You can raise your hand and let me see, or you can type in the chat box. So Professor Abe-san, I have a question. So
Okay, please.
The Lamian Pro, because it cannot derive the temperature. So that's why you have a new instrument to try to divide the temperature of an ionosphere. Is correct?
Yeah. Of course, Lamian probe can provide information on electron mainly.
Okay.
But in order to study various phenomena in the ionosphere, we need to know ion drift. That's why we decided to develop ion instrument. Are you asking?
Yes. So
Okay.
this new instrument had already installed in any spacecraft or any rocket or any
Not yet, but next year we are going to install this our instrument on Japanese landing rocket.
Okay.
Next year. So we hopefully will be able to get new data from our instrument.
Okay. Okay. So if not, so we thank Professor Abe-san again.
Okay. Thank you very much.
Okay. Thank you. Okay.
Thank you very much.
Thank you. So we ended the talk.
Okay.
And
Okay.
thank you for all of you to attend these wonderful lectures. Thank you. Bye-bye.
Bye-bye.